Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to talk about a really important theorem in Calc 3 called Green's theorem. And a lot of times when students learn Calc 3, this thing, along with something called Stokes' theorem and something called divergence theorem, are always taught like really quickly at the end of the year, and students don't really get it, and then the semester just ends, and that's it. Luckily, we have the time to really dive into this and really make some sense of what's happening and go through a lot of examples and all sorts of stuff. So the way I think about Green's theorem and the way I think you should think about Green's theorem is basically what I have right here. So, in Calc 1, right, you basically learn that like this fundamental theorem of calculus where if you want to do the, like a definite integral from like a to b, right, of like f of x dx, right, you can just do, the endpoint f of f prime of endpoint minus f prime of the beginning point there, a. So you're basically just concerned with the boundary of that region a to b, and then you do like subtraction, right? So this is basically the same thing, but for double integrals. So what it's saying, okay, is that if you have a region like D that is some like open, simply connected region. So again, that means like it can't have the holes and stuff like that. And it has a boundary curve C, right, which is piecewise smooth and simple, right? So no like weird loops or something like that, and holes in the curve also. And it's oriented counterclockwise, and we'll talk about the orientation, but basically it's oriented this direction, counterclockwise. So F is just some vector field like PQ here. Then this is Green's theorem. So it says the line integral around that closed loop, so around the boundary curve of like f dot dr, which is the same as this, right? We showed that in a previous video. So this line integral, like around a closed loop, all right, on C, is the same thing as the double integral of the partial of Q with respect to X minus the partial of P with respect to Y. And so it's a double integral of the region D. So D is like the inside, right, of this region or whatever. And really the way that you can think about this is and I actually will try to prove it in a second video on Green's theorem. We're going to spend two lessons on it. You can basically think of taking any region that's like simply connected like this, splitting it up into like infinitesimally small little regions, like I kind of have just 4 here. And then if you do the line integral around the little regions, what you're going to get is, if I like circle that part, when I do the line integral here in this upper left and this one upper right, these two line integrals cancel each other out, right? So you have like 3 line integrals to do kind of to get around that chunk. And then you have, basically 3 here too, right? 1 big one there, 2, 3. And these ones should have the same value, but the negative of each other. And so they're going to cancel out. And you basically just keep doing that. And so you're kind of just getting all these different arrows to go in different directions, and they cancel out. And so there's this kind of like circulation in Green's theorem that naturally shows up because of how you kind of grid out the region like that. And this is something that we're going to talk about in the next section more formally. But this thing right here, actually I should add that it's 2-dimensional curl. So you can have higher dimensional curl also. But curl is actual like vector that we're going to find, okay, later on. But it basically is a measurement of how this like circulation per like unit volume or something like that, or unit area. And it'll be represented by a vector, and we'll talk all about that in another video. It takes a while to explain, but there is a connection in Green's theorem to this like curl this circulation that is happening. That's just down here. This is the same thing, but understood now with curls. So it says Green's theorem states that the line integral of f around the boundary of R, which is the C, right? So like this curve could be the boundary, right? Is the same as the double integral of the curl of f within R. And it really should be called two-dimensional curl, because there is going to be like a three-dimensional curl. And that's it. And so basically this is like the idea. You could have like a region, like this could be your region D inside here, and then C is the outer part. And what's happening is you're having all these different inner chunks, like those two red arrows cancel out. This one and this one cancel out. And so you're going to get all these like cancellations. And so what really matters is the boundary in the end. So you can kind of ignore all the inner stuff, right? And just worry about the boundary. And that's how it is related to like fundamental theorem of calculus, because it's like, if I have some sort of problem where there's like some area here, and I have A and B, right? What I'm basically just concerned with is, the analog that I want you to see is like, what we care about, the blue dots there are analogous to the boundary curve, right? So this is 0-dimensional, these dots. The boundary curve is a 1-dimensional object, right? And then inside here, right, this is analogous to the region D. And region D is 2-dimensional here, and then this region D, let's say, is 1-dimensional, right? So it is the higher dimension up version of the fundamental theorem of calculus. So, the same way you can evaluate this integral, just doing this minus this, you basically can do either a line integral around the boundary or a double integral of the inside. It's equivalent, okay? It just has like a quick refresher down here. These regions would be ones where you could do greens, because these are like simply connected, and those are nice. And basically this one, you could not use greens here. The boundary curve, like even if you shade it in, the boundary curve is not simple because it has that loop, okay? But these are all simple regions. These would be the kind of things you can use greens on, okay? And this is just a funny meme because it's saying this thing is this thing, because that's all greens is. It's just saying this line integral is equivalent to this double integral. And we will use it in both directions. I feel like most often you're going to see that we would rather do the double integral versus the line integral. And I'm going to argue today to you in an example why that is. But technically there are times where you might have this and you want to do the line integral instead. Or utilize something here to help you with the line integral. But I feel like most of the time the line integral is slower to solve. And so we would use greens, pop over to a double integral understanding of it, and then solve the double integral. It's going to be quicker, okay? So one of the most subtle but important parts is right here. Green's theorem has an orientation about it that is important. And this just ties in with the fact that the line integrals, right? When you do these dot product versions, there's something important, because like if you do like the dot product of like a tangent vector here along the curve with the vector field, you're going to get a different sign value if the arrow points that way versus if it points that way, right? Here you're going to get like a negative sign with how this vector field is. And here with this arrow, you would get a positive sign. So, and so the way we adopted it was just that if you move in the counterclockwise direction, math likes counterclockwise, that is what we consider positive orientation. And then if you move in the other direction, you're going to need to do, you're going to need to adjust the sign, because it's going to be the clockwise one will need a negative factored in. And that's what I wanted to talk about right here. So just to sum up again, this region D, okay, this one you could use greens on, that's fine, it's a weird looking thing, but if you can see the arrows there, it is moving in this direction, and that would imply that you would have a positive orientation. This one, going in the opposite direction, okay, that thing's going to have a negative orientation, right? So this is actually an example we will solve, but I just want to set up the orientation part. So what I do first, okay, is, so this is just some vector field, and if I wanted to do the line integral, right, around this triangle, I first want to see what direction things are going. This is like the first thing whenever I do any of these problems that I'm looking into. So I can see I go from 0, 0 to 0, 4. I'm just going to say that 0, 4. To 2, 0, just about right there. And then back to 0, 0, right? So I go this way, right? Then that way, then that way. And so that has, and so maybe I actually will also shade in. So this thing right here has, oh boy, that's embarrassing. I just realized I did like classic algebra mistake. I think I went and I plotted this point and I wasn't thinking when I should have plotted this point. Of course, 0, 4 is not right here. This is 4, 0. So let me start that over again really quick. So this is the correct orientation. Okay, sorry about that. This is the correct orientation. We're going 0, 0, 0, 4, 2, 0, 0, 0. And so this thing, all right, so the orientation is counterclockwise, which means that the line integral of this thing would basically have negative value, okay? So, sorry, and I just went this way, I think. I meant this way. I'm not doing well with this problem. But, so like if we were to use greens here, okay, we would basically not write just the double integral over D. Maybe I'll even color code things. So D is like that green region, right? Of like the partial of Q with respect to X minus the partial of P with respect to Y, dA. We would write, and I'm just going to do blue to make it more clear. We would do a negative, okay? So you would like literally just do it the same way, except you're going to have a negative right there. Sometimes, too, it's kind of hard to see, but in here, sometimes when you're doing greens, because it matters with the orientation, they try to remind you that there's a little arrow right there. So the integral around that like closed loop, right? They're trying to show you that this is positive orientation, is counterclockwise. So if you get a clockwise rotation, right, then that will remind you that you need the negative. So there is like sometimes another symbol, but sometimes they just assume you remember it too. So that actually is like a common mistake. Students might just do this problem and like just accidentally drop the negative and just forget that orientation matters. But what we've adopted is that this counterclockwise direction is positive, and this will just be, we'd introduce a negative, okay? All right, so I actually want to go through a full example now. And so this one is a triangle, again, but a triangle that has positive orientation. So you're going 0, 0, 1, 0, and then 1, 0 to 0, 1, and then 0, 1 to 0, 0, okay? And so we're asked to do this line integral, and it's just around this, like C is the border of the triangle, and D is like the open triangle kind of contained within that curve C. And so this is a good example of why greens is so handy, because if you think about it, all right, this problem, if we were going to do it the way we were doing it back when I first showed you things about line integrals, it would take 3 like line integrals, right, to do this, right? You would literally have to do, let's call this curve 1, curve 2, and then curve 3, right? You would do a line integral around curve 1, and then you add to a line integral around curve 2, and then you add to a line integral around curve 3. And you would have to go through like and parameterize every single thing, right? Which is a ton of time. And now we just literally don't have to do any of that. What we literally have to do is we can just use greens. Maybe I'll do it in green because of that. And we're just going to do the double integral around D. And we just got to do partial of Q with respect to X minus partial of P with respect to Y dA. And so, like, honestly, you identify Q, okay, and we got to identify P, okay, that is important. And I put like the general Green's theorem over here. So the one with the dx is always P, and the one with the dy is Q. And it's saying that whatever is there and whatever's with the dx, whatever's with the dy, you can take the partial of the second one with respect to x, and then subtract the partial of this one with respect to y. And that's Green's. And so my Q is xy, I guess. And then my P, I don't know why I did Q then P, but probably because of this is Q then P. And then P is x to the 4th, okay? And so this problem, much easier, all right? Partial, like then the line integral, because you can just do partial of Q with respect to x. So we would get y, right? Minus partial of P with respect to y, which is just 0, right? And then we're going to do dA, this is over D. And then we just like literally look at this region. It's one that could be a type 1 or type 2. Really doesn't matter. This is where chapter 15 is going to show up so handy. So let's just do it as like a dy dx, I don't know, for no good reason. So if you do dy, you're going to go 0, y equals 0 up to 1 minus x, and then dx ranges from 0 to 1. And if you solve that all out, you'll get 1 over 6. So that is a very good example to show the benefit of greens. I assure you, and I'm not going to take the time because it would like take forever, if I did the line integral around the boundary curve C, I'm going to have to do 1, 2, 3 line integrals, which I have to also parameterize, remember, and it's just tons of work. This is so much easier, and it really, you should just look at it as the fundamental theorem of calculus a dimension up. That's basically what we're doing. We're saying that the line integral around the boundary curve is the double integral within, okay? Whereas in dimension down, this is kind of like your endpoints, and this is like the area between, the endpoints, the region and on the x-axis between them, okay? All right, so I just want to actually go through and solve another one here, basically the one where the orientation was kind of different. It was like backwards, right? So I'm going to set up what we had before and then pick up from there. All right, so this is just kind of what we talked about before, that because of the clockwise orientation, we're going to have a negative in our answer, right? And so, again, it would take 3 line integrals to do this thing, right? Which we then could add together. But instead of doing that, we're just going to do the double integral. So we're going to do the double integral over D, and it's partial of Q with respect to X minus partial of P with respect to Y dA. Q is just this thing, and P is that thing, okay? And so if I almost made the mistake. We're going to need, I'll do this in like red, because it's super important. So because of what I was saying with the negative, like the clockwise orientation, we are going to need the negative of this, okay? So just like I was talking about back here. I'm just going to take my partials and put those in. All right, so, this part right here is my partial of q with respect to x, and then back here is my partial of p with respect to y, right? You do have to do some product rules in there and stuff like that, but just like really right here. But not too bad, pretty straightforward stuff. And then some stuff is going to cancel, which is nice. You got this and this canceling, right? And then you got a minus x sine x and a plus x sine x. So we get double integral d of, again, y, dA, right? And then now you can just look at this and set up your double integral. It turns into like a chapter 15 problem. So, it's another one you can do type 1 or type 2. Let's just go from bottom up again. So let's do, we got a negative again. We're going to do y, we're going to go dy, then dx, okay? And y runs from 0, and then this line is 4 minus 2x. So we got 4 minus 2x, and then we go from 0 to 2 in x, right? And it's another nice one. I'm not going to worry about going through all that. You should be able to solve these things pretty quickly now. So you get minus 16 over 3. So that is just another example where that orientation does matter. It will literally just negate your answer, and it's just because there is a directional part of greens, and it's tied to the fact that, like, when you do the dot product version of the line integral, the direction of the path does matter. If we do the line integrals with respect to arc length, then it doesn't matter. But here, these are the ones where it will matter, the sign. All right, so the last thing I just want to say here with greens is how we kind of use greens to handle some weirder regions. So lots of regions are not what we would call these simply connected regions. You might get a donut kind of shape, like an annulus, and you might get 2 holes in it or something like that. And actually, these have physical meanings. A lot of times these holes can represent like singularities. Like actually a lot of times when you study like things on the scale of like the universe, black holes are weird and they mess up a lot of our math. And the black hole is kind of like literally like the hole right here. It can cause like all sorts of issues and whatnot. But we basically just work around it, and just like with a lot of things with integrals, we can take something like this whole region viewed as one big thing with the issue in the hole there, and we can just basically split it into region 1 and region 2. And so region 1 and region 2 are perfectly fine regions, right? So what I'm saying is like, maybe I'll do it down here. So region 1, this thing is a nice, simply connected region. And so we could do basically, if we want to do greens on this whole thing, we would just have to do 2 problems. We would do that red one, and then we would do this green one right here. And if we do those together, then we basically still have covered the whole region, but we've just sort of tricked it so that we can basically handle all that stuff together. So the idea here is like we can, this symbol right here, I don't know if we've actually seen it this year. It's something called the union symbol, but we're basically just combining the 2 sets is really what we're doing there. So we're like taking C1, right? So this region D1 here is C1 combined with C3. And so this blue line right here is kind of like these dotted lines down here, or this part, and this part. And we kind of just introduce those blue lines, and that's how we like split the region. So the idea is like you're going to do the line integral of curve 1 union curve 3, right? And that's equal to this region double integral over d1. And then if you add it to the line integral of curve 2 combined with minus curve 3, all right? So curve 2 and then minus curve 3 go in the other direction, right? Then it's saying that, now I can do that as the double integral of not d1 and d2, but now truly all of d together, and then, just normal Green's theorem stuff in here. So it gives us a natural way to combine, and the nice thing is, like, if you, this region right here is equivalent to the line integral of curve 1 union curve 3 union curve 2 union minus curve 3, which simplifies because this and this go away, and you get curve 1 union curve 2. And so that's the true, boundary curve 1 union curve 2. And all the orientation works out really nice as long as you split it up in an opposite way like that, like one arrow this way, one arrow that way. Then they cancel out and everything. So that's kind of how we can deal with like these weird holes and singularities and issues. We basically just have to take the non-simple regions and split them up into simple regions. And then as long as you're careful about the orientations and all that, it'll all work out. So just to kind of show you an example of this one. So if we have this region, there is a singularity basically at the origin, because you got the division, right? And so we want to show that this thing equals 2 pi, this line integral equals 2 pi for every positively oriented, so counterclockwise, simple closed path that encompasses the origin. All right, so this one's pretty tricky, but the idea is like, imagine like an infinitesimally small circle right here that goes around the origin, and like this circle is just going to have like radius a, where a is like infinitesimally small. What we're going to do is like that is going to kind of be like the circle in these problems, and we're going to set up a region where we can go around this actually in opposite direction. And so instead of going, this is like the normal positive direction, we're actually going to go this way. So just like in this picture, then you can cut it, right, and combine those two and get the full region. And then this C is like an arbitrary simple closed path, basically. So this doesn't have to necessarily be that shape or whatever. But basically, if we set it up that way, where we have a circle here, and then this is just like an arbitrary different closed curve, we can really do the line integral this way. So we can do line integral around arbitrary C, right, of like p dx plus q dy is gonna, if we add to that the line integral around minus c prime there, the circle, okay, p dx plus q dy, then that should equal the double integral by Green's of partial of q with respect to x minus partial of p with respect to y dA of d, the whole thing, right? So the idea is like we've cut it so that we're going opposite around this way now, so it's negative in there, and that should give me the full double integral. So I'm running out of time here, but that's kind of the setup of this one. And then I'm going to do another quick video where I actually compute this thing and show you that you would get 2 pi.